second session this morning on optimization. I'm Alan Edelman, and I'm a professor at MIT. And what I like to joke is that it's great that there are so many people contributing to Julia all around the world. And what I joke with my colleagues at MIT is that MIT is sort of the last place in the world where people are using Julia, with the exception of Iain and Joey here, who are using Julia optimization. So do you want to continue the tradition that your house started and say how you became a Julia person? Okay.
So I think I saw like a post on Hack and Use sort of pre 0.1, maybe even, and I thought it was pretty interesting. And then Miles, who was also a PhD student in my group, started a year after me, and we sort of started talking about making a modeling language. And we got stuck in and realized it was actually really, really good. And then Joey came on board, and we've kind of just been evangelizing Julia ever since. I came from like a world where I was using Python and C++ and sort of flipping between them based on like the task at hand, and like just write it in Python, get frustrated, and rewrite it in C++. And now I just write it to Julia once, and it's made my life a lot better, really.
Yeah, maybe I didn't say it as clearly as I might have, but we didn't meet until what? Months or years?
After. Yeah, no, it was like entirely independent. Yeah.
Right, that was my point, right?
Yeah. So that's me.
Yeah, and I was a serial MATLAB user all through undergrad. I'd heard of Julia before, and actually, so I found out that these guys were working on this project, and I got a little bit more invested, and yeah, it's been great. So I've been using it for roughly a year now. Yeah, I guess we can get started. So I'm Huchette.
I'm Iain.
And we're both graduate students at the Operations Research Center at MIT. And today we're going to be talking to you about JuliaOpt, which is a collection of optimization packages for Julia.
Can you speak up?
Yeah. Oh, yeah, sorry. Okay, so it's probably best to start off with the description of what exactly mathematical optimization is, what we're trying to tackle here. So kind of in its most generic form, mathematical optimization problem is you have some decision variable x, lives in some space, and you have an objective function f, which essentially scores your values for x. Right, and so you want to pick the best value you can choose to minimize your function f, and it's subject to a certain set of constraints that you have to describe your problem. Right, and so the description on the last slide was kind of hopelessly generic. Right, any solver that's actually going to numerically try to solve your problem is not going to work with it in that form. So it's really helpful to kind of try to describe in more detail the structure of your particular problem. So there's all kinds of flavors for different kind of optimization problem. Kind of the most central dichotomy might be between constraint problems where you don't have any constraints and constraint problems. There's also issues with whether your variables are continuous or discrete. If you have a combinatorial structure, maybe you don't have derivative information for parts of your problem. But it's really, the central idea is it's really important to be able to understand kind of the structure of your problem, because the solver is going to be able to exploit that and be able to solve your problem much more quickly. But kind of from a user perspective, what you really want to be able to do is be able to express your problem in code that's kind of a natural and maintainable translation of the problem as you would write it down on a piece of paper, right? And so ideally what you want to do is try to decouple that as much as you can from how the solver is kind of handling things internally, and also kind of try to decouple it from the data that you're using for a particular problem. But this has really kind of come to loggerheads with how the solvers are actually working internally, because they're really exploiting this problem structure to actually solve the problem efficiently. And different problem structures are going to dictate different kind of data structures that they're going to want to take as input, right? So with that in mind, we're going to split our talk into kind of two halves. In the first part, we're going to talk about JuliaOpt, which is the organization, and kind of some of the packages we've been working on under that umbrella. And in the second part, we're going to talk about what exactly it is about Julia that we find really cool and has made our lives easy when we're trying to develop these tools. Right. So JuliaOpt is a collection of high-quality optimization-related packages for Julia, and we really want to try to emphasize the first part. Right? We really strive to produce high-quality packages. We want to make our documentation really useful and kind of extensive. We want to have extensive test suites. We really try to have cross-platform support, especially for Windows, which is very tricky sometimes. And we try to use bin-defs a lot, because some of the installation and build issues with these numerical optimization libraries can be kind of hairy. So it's really nice to be able to hide that from the user so they don't actually have to worry about it. We have a website, a GitHub organization, and also a mailing list if you guys have any questions about Julia or optimization. So as of June of this year, we have, I think, 10 or 12 packages that can fall under our umbrella organization. Today we're going to talk mostly about these 7 that I've highlighted, and specifically kind of how they form what we call the JuliaOpt stack, which kind of has 3 levels. We have a high level, which is jump, mid-level with the math base, and a low level kind of a solver interfaces. We're going to talk about each of those pieces separately. And so at the bottom, we have our solver interfaces. So there's hundreds, there's tons of kind of optimization software that's out there, and people have spent years and years, put a lot of effort into making these solvers robust and efficient, and so we really want to stand on the shoulder of giants, and it's not kind of the first order thing you would do is not to try to recreate this. You really want to be able to leverage it for your particular applications. So we have kind of an extension of these wrappers around C APIs essentially. And there's nothing particularly maybe interesting about how we go about doing it, but it really is vital for everything else we're going to talk about for the remainder of the presentation. And at the top we have Jump, which is our algebraic modeling language written in Julia. And so you guys might not be familiar with what exactly an algebraic modeling language is, but you might have heard of some of the other players in the space. So there's YAML, which is in MATLAB. There's Pulp, which is in Python. There's Amples and GAMS, which are kind of their own standalone things. And there's also CVX, which is kind of fundamentally different from what we're trying to do, but it has many of the same goals and philosophies. And I think Madeline's going to talk about those in the next section. So essentially what an AML is, an algebraic modeling language, is a tool that allows you to kind of try to write your problem in the closest form to actually what you would write on a piece of paper when you're writing it mathematically. And the job of the AML is to actually take that and translate it into the sparse, specific data structures that the solver, the low level, wants to take as input to actually solve your problem. Right? And so really the selling point for these kind of tools is that it's much, much easier to reason about this kind of quasi-mathematical expression of your problem than it is to reason about the particular data structures that you're generating. Right? And in a minute I'm going to go through 2 examples to kind of illustrate that. But first we're going to talk about the jump philosophy. Right? It's kind of a 2-pronged approach. And so what we really want to do is, on one hand, make it really easy for a practitioner that doesn't really maybe know so much about the internals of how the solver is actually working at a low level, but really just wants to be able to plug their problem in, get an answer, and go about their day. But at the same time, a lot of these solvers really expose powerful tools if you know what you're doing, if you're a domain expert. But usually these are only available through kind of a low-level C interface. And so we want to expose those to advanced users, but still make it easier for kind of newcomers or novices to use the tools.
Can I just say that for me it was a mind-blowing experience that matrices are not the most natural way to
Yeah, well, I mean, at a low level they are matrices that are being passed to the solvers, but yeah.
Yeah, the matrices are further below.
Yeah. But yeah, and through all this we want to make it as fast as possible. So the first example, probably something you guys are all familiar with, is solving a Sudoku puzzle. To kind of refresh your memory, you have the numbers 1 through 9, and you want to place them such that each row has every number, each column has every number, and each of the 9 kind of bold subgrids has every number from 1 through 9. And so you can model this as an integer optimization problem by defining variables x sub I, j, k, and say that it's equal to 1 if and only if you place value k in cell ij, right? So kind of describe a couple of the types of constraints that we're going to define our integer program. And so on the left here we have a constraint, or a type of constraint that says that all numbers have to appear in each row. Right? So we have a nice algebraic description of that, essentially just a sum. And we have some indexing that's going on. And on the right here we have the constraint that says all numbers have to appear in each subgrid. And it's essentially the same thing. We're taking a sum, we're just kind of tweaking the indexing a little bit. It's a little bit more complex. But it's essentially the same kind of constraint. And so now we can actually go and see what the syntax is going to look like for describing this type of constraint in Jump and Julia, and how actually Groby suggests you do it using their C API. right? And so on the left, we have the jump way. We have a macro add constraint. The first argument is a model object, a jump model object. The second is kind of a way of describing or indexing into the constraints. So what it's going to do is introduce into the namespace of a type constraint ref named row that you can index into by I from 1 through 9, k through 1 through 9. And the third argument is actually giving me the semantics for the constraint. We're saying we have a variable object x. We're going to take a slice along the second dimension, take the sum of everything, and set equal, or require this equal to 1. And so it's kind of very similar to the way that you're actually mathematically describing that constraint.
I would actually say that's clearer to me.
Yeah, no, it is. It is. Yeah, and on the right here, we have the way that you would do it using the C API for query. And we have 3 for loops going on. They each have their own index. We kind of have some weird incantation here to describe the particular index. So essentially what they're doing is they're working with the low-level matrix. They're describing this constraint as essentially a row in a linear system. Right? And so end is kind of a sparse representation of the index in that particular row, and the val is just the corresponding value. Right? And so what I really want to emphasize here is that this is kind of inherently tied to the way that the solver represents the data internally. Right? And so if all of a sudden I decide I want to embed my Sudoku problem in some kind of general nonlinear problem, and all of a sudden I want to change the solvers, this isn't going to work anymore. I'm going to have to completely rewrite this code for that particular solver. Right? And so it gets even worse if we go to the second type of constraint, right? The subgrids. And so on the left we have the jump semantics, and it's essentially the same thing, we just change the indexing to match up now. But in the C example, now we have 5 for loops. They each have their own index. And if I were to just give you this code with no context, I doubt very strongly that you'd be able to figure out what the hell's going on here. And yeah, I mean, you can imagine that if like there's a bug introduced somewhere, if you're off by 1 or you have a typo, it's going to be really hard to debug what exactly is going on.
Can I ask a really dumb question?
Yeah.
Wouldn't even the left side be simpler if you treated the Sudoku puzzle as a 4-dimensional 3 by 3 by 3 by 3 array rather than a 9 by 9 grid? Because I'm looking at here and I'm trying to remember who's the row, who's the column.
Obviously, much Sorry, 4 by 4.
We have a 9 by 9 by 9 grid right now.
So you're saying 3 by 3 by 3 by 3.
Well, what is the third? Well, we could discuss it later.
The dimension is the number.
Sorry?
It's like the first dimensions are like spatial, and the third one is like the...
Oh, so I guess I'm saying 3 by 3 by 3 by 3 by 9. Might be more natural.
Yeah. For this one, though. Yeah, okay.
Yeah, that's hard to read in a way.
Yeah, so actually
is subgrid something that's in the environment already, or that's not a special construct of
no, so we're really using the macro capabilities here, right? So what it's going to do is it's going to generate. Actually, Ian's going to talk about this a little bit, but essentially it's going to generate a bunch of code that's going to define something we call a jump dig of a type of called constraint reference, which essentially is going to reference a particular row in the problem specification. And so essentially what he's going to do is introduce this variable in a local namespace, right? And so you're going to be able to use subgrid in kind of your Julia code after you define it. And we also have similar things to define variables. And so it's a macro called defvar, and it introduces like if you say defvar of x and index into it, you can then use that variable x later on when you're adding constraints, things like that.
So does that mean that this is a non-hygienic macro? Adding variables into or referencing variables in your local scope?
Yeah, in that sense, but
Yeah,
it's a very
sometimes
useful.
non-hygienic macros are exactly what you want.
Yeah.
Yeah.
So I have a question. Here it looks like you could wrap the add constraint inside a for loop
Yeah.
in order to iterate over ijk. Is this going to be more efficient than doing it that way?
So it actually, this method is doing exactly what you're saying. It's
I see.
generating a bunch of for loops and then calling add constraint.
It's the same.
Yeah, it's essentially the same. It's just, I think it's a little pithier because you can actually just do it in one line as opposed to actually nesting it. Yeah, it's essentially exactly the same. Okay, and so now I'm going to go on to a second example, which is more of a real-world practical problem. So for the past couple of weeks, I've been working with Argonne Lab here in Chicago, and their Department of Energy lab. So they're actually very interested in trying to model the electrical network, in particular, kind of how variability in wind power kind of affects pricing in the electric power network. And so there's kind of a smart way you can try to model these types of problems, and they have kind of a custom solver that exploits the structure, and they can kind of get these nice scaling results in their large parallel systems. And so in JUMP, what we can do is actually model the problem in about 50, 70 lines of code, and actually a lot of that is actually just the data wrangling, getting data onto the nodes and doing things like that. And there's about 500 lines of glue code, which essentially takes the JUMP representation of the model and translates it into the problem data that the solver wants, which in this case is essentially callbacks that generates white sparse matrix systems. And we can compare that to the C++ driver they had before that, which is about 2,300 lines of code. And so the example with the Sudoku from the slide before, imagine like orders of magnitude more complex than that. Like it's incredibly hard to parse what's going on. And I guess even more importantly than that, it's not generic in the sense that the JUMP code that we have, the 500 lines of glue code, that's reusable for any particular problem you'd want to be able to pass to the solver. Right? You can completely change it. You can add new constraints. You can mess with your problem all you want. Where the C++ code is really only reusable in the sense that you can copy paste it and then try to tweak it to kind of try to handle what your new problem is. Right? So it's we really have this added benefit because once that 500 lines is in place, you can essentially model whatever you want and pass it. So it can be really, really powerful. It's much easier to reason about 50 or 70 lines of code than it is to reason about 2,000 lines of code. So it's massive.
So I'm going to first talk about this other layer in the pie called MathProg base, which is kind of dull but very important. And that it's a common interface to all these solvers. And it also has some functionality exports that you can kind of use directly, such as limprog, which if you're a MATLAB user, you've probably seen before. So what it does is, basically it defines some abstract types. Maybe the most easy one to think about is this abstract MathProg solver, which basically is an abstract type that all the different solvers implement. And we have a sort of a big body of documentation and sort of fallback methods, which you can just keep on implementing until it works to basically define the interface for a new solver you create. So it's simple things like add a constraint, or add variable, or remove constraint, or get solution value, or get objective value. So the benefit for users of having this like nice, clean, abstracted layer is that they can ignore the solver details and basically sort of achieve that aim of decoupling the problem from the specific solver. And for package developers, it's also good because it allows them to sort of jump into this JuliaOpt ecosystem rapidly. So the kind of workflow would be to create a one-to-one wrapper around your C or C++ sort of solver, and then build a MathProg-based interface on top of that. And then suddenly you've got it open to the kind of entire JuliaOpt ecosystem to use. So that's we currently support sort of following kind of problem classes. So there's linear problems and mixed interlinear problems, which are kind of the bread and butter of like operations research and management science and things. And we've also got some sort of newer types of problem classes, such as quadratically constrained quadratic problems, where the constraints now quadratics of the decision variables. And also semi-definite programming, which is basically linear constraints and semi-definite constraints. So you say like the decision variables lie in the positive semi-definite cone. And coming soon to MathProg base are a general interface for constrained nonlinear solvers, such as IPOpt and Nitro, as well as a conic interface, which is kind of Madeline's going to touch on what that's all about. And I just wanted to emphasize that Julia makes wrapping these C libraries very simple. So IPOpt.jl is a wrapper for the nonlinear interior point solver IPOpt. And the entire interface is about 370 lines of code, of which 50 or so is a MathProg-based interface. So that's pretty lightweight. The closest comparison would be the Python interface, which is a hand-generated nightmare of 1,300 lines of code, which is just impenetrable. It's all this sort of boxing and unboxing, and it's a very callback-heavy solver, and it's just scary to look at. Whereas you can look at the Julia one, and it's very obvious. It's almost like a natural translation of the header files. The other cool thing about MathProg-Base is, I think, the composability of the solvers. So JuliaOpt has solvers for mixed integer linear problems and convex quadratically constrained problems. But this new kind of problem that's sort of generating a lot of papers lately is these non-convex quadratically constrained problems. And non-convex problems are generally very, very hard to solve. So the solvers are coming, not really there yet, very experimental academic kind of solvers. So if you want to play with this on your own, it's kind of tricky to get it set up and installed. And so I thought, well, wouldn't it be nice if we could have a Julia one? So Jump can model these problems, and they can be solved as a sequence of mixed integer linear programs. So I thought, let's make a solver in Julia. And by leveraging all the existing work in MathProg-Base, I was able to make a solver for this new problem class of 400 lines of code simply just by taking Jump's input, filing it into a for loop, basically calling mixed integer linear programming solvers through MathProg-Base. So it's this idea of composability that I think is pretty exciting, and I'm looking forward to seeing more solvers made in Julia that kind of distribute the workload and solve many mixed integer linear problems and keep it all abstract without any performance penalty. Quick mention to the other JuliaOpt packages we don't have time for today. Optim.jl is Julia's workhorse for sort of simpler optimization problems, so unconstrained and box constrained. And this is classic line search, Newton things, and I think Tim's been working on a interior point solver for that as well. So hopefully more complex constraints coming along soon. NLOpt is an interface to the NLOpt solver written by prolific contributor Stephen Johnson. And that's solves a lot of different kinds of problems and is a great thing to have readily available. And a newish package, least squares fit, is sort of the least squares part of Optim broken out into your own package, and that's going to be in metadata soon. And we're always looking for more packages if you have one you want to tell us about. So the second half is why Julia. So what makes Julia good for? Oh, we're good. Oh, we're good. All right. So what makes Julia good for this kind of work, and what's made it such a pleasure to work with? So something that Joey made reference to is that we are using these macros to generate efficient code, so you don't have to. So Jump makes a lot of use of this. So here I'm saying I've got some variable xij, and it's in the set of positive integers, non-negative integers, and it's indexed over two sets. One of them's a nice set of numbers, 3, 4, 5, your range. The other one's an arbitrary set of things, the colors red and blue. So in Jump, you'd write this like this. You'd use this def bar macro with the first argument to model. The second argument is the name of your variable and its index sets. So the range 3 to 5 and the set of items red and blue. And that they're non-negative and that they're integers. And this injects this code into your local space where it defines this new variable x, which is an instance of a jumped dict. And a jumped dict is it's like a dictionary, but more general with some special cases for things like ranges. So for example, if we're indexing by a range, and so internally we store a big matrix basically of variable objects. And jump dict is basically a wrapper around that matrix. So when you index by a range, Jump can smartly look into this matrix to find the corresponding variable because it can just do a constant offset from the range. But for the index sets, you need to use a dictionary to kind of figure out which index in the matrix corresponds to this variable. So we generate all this code dynamically, and we also generate access methods for this jump dict that we generate, such as getIndex. So we can write things like get the value of x for comma blue. So that's.
So is C+ just greater than 0 in your world? Is that a bug? Or is it greater or equal to 0?
I'm going to say it's greater than equal to 0 this time, because I didn't think about it that hard.
Over in the math department, C+ is greater than 0.
Yeah, that's loose, sustained. I should have hedged and just been like 1 or something. So I wanted to, it's hard to show you the code we generate from a macro because it's generally not, there's lots of gen-simmed names and things, but here's another thing we do with add constraint, which is also a macro. And here we're saying add a constraint that says, the sum of xi from 1 to 9 plus another variable x is equal to 10. So the sum of the curly brackets is some special jump macro language, where it's basically, Julia doesn't have array comprehensions with conditions, but this is something really needed. So what we basically did is make our own little array comprehension with conditions inside Julia using metaprogramming. So we haven't used it here, but you could put a semicolon here and put a condition, and basically there's a filter on which variables are included in this sum. But here we haven't done that. We've just got the simple sum. And so what this code generates is basically the following. It generates, we're basically describing a row of a matrix in a sparse representation. So we need a vector of indices and coefficients. So we make two empty arrays. And the macro says, well, this sum is over this set, and the length of this set is going to be stored in len. And we pre-allocate the memory for it once. And we then build up the sparse representation of the row by pushing on 1, x1, 1, x2. And then finally we push on one extra term for the s, which we couldn't pre-allocate memory for because we're not that smart about analyzing the structure. So we have to do like one reallocation maybe. But otherwise it's pretty memory efficient. And then we add the constraints to the model. So the reason I'm kind of emphasizing the memory stuff is that what most other modeling languages do that are embedded in higher level languages is they use operator overloading. So and here I say, well, my x is of type jump.variable. So maybe I overload the meaning of plus to now support number plus variable, or variable plus number, or variable times number, and so on. And I build up a representation of the row sort of piece by piece. So number times variable is a row with just number variable, and then I add these two together and add them together. Lots of memory allocation is my point, and lots of general sort of temporary intermediate representations. But what Jump's doing is sort of just-in-time, compile time, whenever the math programming happens. It's analyzing the statement and it's efficiently generating the sparse data structures. And the benefit of this is that we basically have low memory churn, and we get as fast as these standard commercial algebraic modeling languages. So we're basically saying that our domain-specific language embedded in Julia is as fast as a purpose-built language for this, thanks to macros. Another feature that we make a lot of use of is callbacks. So a lot of solvers, especially integer programming solvers, allow you to tinker with the kind of process of the optimization with callback functions. And in Python, for example, if you're doing this, there's a lot of churn, and it's an expensive interface. It's not super lightweight. So if you have to do this a lot, you're paying a price for all the time spent going between Python and C. But with Julia, it's as simple as just wrapping a function with a C function usingccall. And we use this to solve the traveling salesman problem, which is a kind of a hard problem in a computer science sense, where you're trying to find a trip through n cities that's the shortest as possible where you end up where you started. And we can write this down as an integer optimization problem with linear constraints. But unfortunately, it has an exponential number of constraints. And these constraints need to eliminate subtours. Also, I guess it's reassuring that it has an exponential number of constraints, because it didn't in IOP. Proving some pretty cool results, I guess. So we have an exponential number of constraints, but the insight we gain is that we don't need them all necessarily to enforce the optimal solution. We probably need them all in one specific case, and that's why P doesn't even need them. So what I mean by subtours is that if I just say you have to visit all cities once and once only, but I forget to mention the subtour elimination constraints, what it will do is it'll say, oh, visit these 3 cities and these 3 cities, visit them all once, what's your problem? But the problem is that we've now got 2 different trips, they're not connected. So we have to add a constraint that says, well, you have to leave this cluster of 3 once and leave this cluster of 3 once. And if we enforce that constraint, these ones will break and these ones will be enforced and we'll get an optimal tour. As you can imagine, there's 2 to the n possible of those constraints for each possible subset of cities. So we add these. We write a jump model that only has the constraints to enforce that you enter and leave each city once, and then write a callback function in jump that operates on these jump variables and adds the constraint you need just to break the current solution, break the current subtour. Thanks. And the advantage of Julia, I guess, is that it's very low overhead for this sort of C interrupt, so it's quite high performance. And then the jump advantage is that we're able to do these solver callbacks in a completely solver independent way, which as far as we know, no one else has ever done in another modeling language. So you can switch between Garobi and Cplex and hopefully skip soon, swap them out, and the same code, your code will keep working, but you'll get the benefits of the different solvers and their performances. And finally, derivatives. So optimization methods generally perform much better when derivatives are available, and there's usually two ways to get them. You either provide them yourselves, which is painstaking sometimes, and easy to make mistakes, or you estimate them using finite differencing, which is inefficient and inaccurate, so that's not very good. But a lot of people do it. You see it a lot. It's kind of people's easiest thing to think of, I guess, so they often go to that. JuliaDiff, which was recently announced, is a sort of organization that's related to JuliaOpt. It's all about calculating derivatives exactly. So there's sort of two groups of packages. There's joule numbers, hyperjoule numbers, and power series, which create new data types. And if you write your function in a generic way, these packages will basically calculate the exact derivatives of your Julia code, which is a revelation. Once you try it, you won't go back. Reverse diff, sparse, source, and overload are another cluster of packages, and these take a different approach to differentiation. They actually operate on the syntax tree directly, and as does the calculus package, which is kind of a simpler version of some of these. And they basically differentiate your code, not using types, but just by analyzing the structure of it. And this is being used today in other packages. So Optim, you can set autodiff equals true, and now you have derivatives of your function, supposedly if you wrote it in a generic way. Jump uses reverse diff sparse to calculate sparse Hessian matrices of large nonlinear optimization problems, and it's very not trivial. Miles Lubin, who's our collaborator, has done a lot of work on that, and it's a thing to behold. It's like graph coloring in there, and it's just crazy things. And MCMC uses reverse diff source to calculate gradients of statistical models. And who's using JuliaOpt? Well, the only way we can really tell is by our Google Analytics numbers. So JuliaOpt.org has had 541 uniques in the last 30 days. Jump documentation has got 493, so a lot of people are checking out Jump. And Matplotlib has had 93 hits. And coming up next in JuliaOpt, hopefully constraint programming and some of the cool things that are available with Skip, which is Solver. Jump is still adding features, so SDP modeling, Joey's been working on that for a few months now, and hopefully that's going to be coming soon. Pre-solve and reformulations are ways to sort of take the model at the jump level and change it around in a way that Solver might not be able to do to make it much quicker to solve. And discipline convex programming is another kind of modeling technique, and Madeline's going to talk about that right now. And also, we're interested to see if Solve is written in pure Julia, especially leveraging distributed computing, start appearing more and more, and hopefully get interacted and incorporated into this kind of framework. And that's it. Thanks so much.
Perhaps you could update me on what's new in automatic differentiation, because one of the issues with providing your own derivatives is oftentimes you can analytically eliminate zeros or identities that would be hard to derive from automatic differentiators. So is there progress in this one?
Yeah, I mean, I know that at least for the reverse differentiation packages, they are pretty smart for that. I don't think that the joule numbers stuff can do that necessarily, but yeah, the reverse diff ones are very clever and how they increase sparsity of the problem, especially.
Miles would know about that. This is his baby.
Yeah.
So maybe
Just dabblers.
I'll ask about that as well. So there are all these automatic differentiation codes out there. I've never looked at them, but I know they exist.
Yeah.
You're not using any of that.
No. So none of the stuff that JuliaDiff has is calling out to. There's something called Casati that we were looking at. That's kind of a reference point. No, it's all pure Julia so far, and I think it'll stay that way because it's very much integrated into Julia's meta programming features, and that's almost like the edge. So Miles' opinion, Miles is our collaborator on this stuff. He's of the opinion that Julia kind of represents a brand new opportunity for automated differentiation. It's never been easier to be high performance, but also accessing the code. So it's kind of all the things people did see that were kind of scary. Yeah, probably shouldn't have been done. Now we've done it, it's going to be okay.
not really a question, but as someone who doesn't really know, I've never been an expert in any of these solvers, but I've looked into using them for stuff, and they always have these like terrifying interfaces that are impossible to figure out. So I can't overstate how awesome it is to have an interface that's reasonable, that is like not specific to a particular solver, so you can just swap them out. And, start with one of the free ones, and then later be like, you know what, I want to pay for a better solver.
That switch between commercial and open source solvers is something people face all the time in both directions. Like academics have access to these commercial solvers for free licenses. You want to go give it to someone? I've seen it happen, and then people have to do rewrites basically, and then they reintroduce bugs, and it's very inefficient. But now you can just swap it out.
With optimization, there's always the hairy part of when do you terminate, what are these, all these parameters. I think I remember seeing 20 different stopping criteria. How do you deal with that intrinsic issue?
So we actually have kind of hunted on that one a little bit. So we let you pass the solvers for the specific parameters through. We haven't tried to abstract away those sorts of things. There's some things that are simple, like time limits. We could probably support in an abstract way, but tolerances tend to be too.
But even just termination tolerances, there definitely are some shared kind of parameter values that we could abstract to let. But yeah, there's Cplex or Ruby expose tons of parameter options. We're not going to be able to.
IPOpt is 5 different line search parameters alone for each kind of flavor of line search you pick. So. Yeah, it's best. We make it easy for you to talk directly to the solver to pass those parameters, but we haven't tried to kind of wrangle the beast.
Okay. All right. Well, thanks again.
Thank you.